Guys, the next piece of equipment that I want to talk about is called the polarimeter. And the reason is because this is going to follow the density meter that we've already discussed in a previous course folder, okay? And the reason that it's going to follow that one is because this is also made by Rudolph Research. So, what perfect way to kind of follow up that density meter, because that was made by Rudolph Research, with another piece of their equipment that we have in our laboratory called the polarimeter. So, I want to talk to you about what a polarimeter actually does and what its purpose is and why we would use it. But you're eventually going to refer back to the same website, okay? The same website that was used for the density meter. If you go back and you go to the home page, you're going to see the product line that's going to be listed. The density meter we've already talked about. So now we're off to the polarimeter, which is right here. Okay, so I'm going to talk to you a little bit about our polarimeter, what it does, what its purpose is, and then we'll go back to the website and we'll revisit it and talk about some things that are specialty for Rudolph Research. Okay, so the first thing that you have to understand is that organic molecules, and organic basically means carbon-based. These things are just like you. Some of them can be left-handed, and some of them can be right-handed. A lot of people are surprised when they learn that. But 3D orientation is very important in our field because it can mean the difference between life and death. Just like thalidomide. Thalidomide was a drug that was prescribed to pregnant women for morning sickness. Well, during some of the testing, it showed no hazards, no health effects that we needed to be worried about. And then by the time it was released to market and by the time that women were starting to go into labor to have their babies, we realized that they were having deformed babies. And the reason is because of the drug. We did not fully understand that molecules at that time had a left-handed version and a right-handed version, and they could be completely different. Even though that they were made up of the same number of atoms in the same way, the 3D orientation was different. It was just like your left hand and your right hand. They're still hands, right? They look the same. They look similar. One is a mirror image of the other one, though. So in actuality, they are not identical. Molecules are the same way. They are not identical if they can come to you in the form of a left hand or a right hand. Your feet are the same way, right? Both of them are still feet. They both still do the same job. They're both probably made up of the same stuff, but one is just the mirror image of the other. Again, molecules are very similar. Well, not only that, but a molecule can rotate light. So if they are left-handed or right-handed, then these molecules can rotate light. Basically turn it on itself. Okay? Now, the problem here is that a lot of people mistaken, and they think that right-handed molecules only rotate light right-handed, and left-handed molecules can only rotate light left-handed, but that is not true. Okay, so down here below, I'm going to put for right-handed molecules, it can turn light one direction or another. And left-handed molecules can do the same thing. So it can turn it in one direction or another. They don't have to match. A left-handed molecule can turn light left-handed, and a right-handed molecule can turn light right-handed. Doesn't matter. Does not matter. So the plus is what we would typically use for right-hand turn, and the minus is what we would use for a left-hand turn. Well, what do I mean by that? Well, let's say that we are looking down a tunnel. Okay? And let's say that at the end of this tunnel is a light source. This molecule can take that light source and turn it right-handed. And if it does, that is what we call the positive orientation. Well, it can take that light and it can turn it left-handed. And if it does, we call that minus. So, a molecule can be left-handed or right-handed, just like your hands, just like your feet. So let's say we have a left-handed molecule. We put that molecule into a polarimeter. The polarimeter measures the rotation of light. That is what it does. So the molecule goes into the polarimeter, we turn the polarimeter on, and we allow the molecule to do what it needs to do. And the polarimeter will pick up, oh, this molecule turned the light, and it turned it right-handed, so it's a positive number. Or it turned it left-handed, so it's a negative number. And not only that, but it will actually give me a measurement. There will be a number associated with these. It will be positive 0.63, or negative 1.27, or positive 62.4. That will be on the readout of the instrument. But that's why we would use a polarimeter. We know that it's going to be rotating light. All right, so if I kind of want to draw a schematic of the polarimeter down here at the bottom, what would happen is that I would typically have some type of long cylindrical tube, and this tube will have an inlet and an outlet on it. So that same syringe that I could use in the density meter, I can use that in the polarimeter as well. So what happens is that I would take that syringe, I would suck up some sample with it, I would walk over to the polarimeter, and I would put the syringe on one of the outlets, it doesn't matter which one, and I would slowly push the sample into what we would call the polarimeter cell. So this would slowly fill up and it would come out the other end. Okay, well, I want it to come out the other end. I want the cell completely full. All right, on each end of the cell, there's going to be a small window that's going to line up with each other. So this is going to be a glass window that I will be able to look through. So once I load my sample up, what I would do is I would take my polarimeter cell and I would look through it with my own eyeballs. And if I can see straight through it, then the machine can see straight through it. That's good. That's what we want to see. Okay? The problem is that if you don't load the polarimeter cell up the proper way, you can create air bubbles. We saw that air bubbles was bad in the density meter. Air bubbles are going to be bad again here. Those air bubbles will take up space and it will create an air pocket in the polarimeter cell, and this will become very cloudy or very vague. I will not be able to see completely through it, and I do not want that to happen. Okay? The solutions can have a color. That's no big deal, but they need to be clear. If they're not clear, the polarimeter will not work, and air bubbles will distort that view. And I cannot have an air bubble in the polarimeter cell. If there's air bubbles, the way that I fix it is I just keep pushing more and more sample through until it pushes out the air bubble and it's no longer present. All right? So on one side of this instrument, I will have a light source. And on the other side of this instrument, I will have a detector. And what happens is that I would put the polarimeter cell in here with maybe just the solvent in it. Okay, some type of liquid that has no molecule that will turn or anything, just to blank it out. That's really all that we would do, just to get a reading of a 0. So the light source I would cut on, the light source would go through the polarimeter cell, and it would line up. And the detector would say, hey, I see some light coming through and I didn't have to turn anything at all. So because of that, the reading is going to be 0.00. So then my sample would go in. And let's say that the sample does not rotate light. Well, the light source would come on, the light source would go through the sample, it would go out the other end, and the detector would see it. And it says, hey, I did not have to turn. And because of that, the reading is 0.00. This sample does not have a rotation. Some of them don't. Some of them do not rotate light. That's okay. Not everything has to. All right, well, let's say that I go into a sample and it does rotate light. All right, well, up here at the top, what I'm going to do is that the sample will come in only one direction. So here's the sample tube. And then here is the light that comes in one direction only. So as it goes into the sample, what begins to happen is that the sample begins to turn the light in a different direction. And the detector over here on the side says, wait a minute, I was oriented straight up and down because that's how this light's supposed to come in. And because this light is now turned, it's not coming in to the detector anymore. It doesn't fit. It's like that old game that you used to have maybe as a kid. You know, can you put the round peg in the square hole? And the answer is probably no. That's what the polarimeter is doing here. I'm trying to squeeze a round peg in a square hole and it's not going to work out for me. So the detector makes the decision. Okay, it's not coming through the way I'm oriented right now, so I'm going to slowly turn myself, either left-handed or right-handed, in order to get the light to come through. And this detector will rotate. It will twist, it will turn until it sees the light. And just like in Poltergeist, when it sees the light, it will stop and everything is good in the world. Come to the light. Well, depending on how much it turns, that is my readout. So let's say it's 3.21. It's 3.21 degrees. That's what we understand that number to be. And there will be a positive or a negative up here to let you know which way it did turn on itself. Did it turn left-handed? Did it turn right-handed? Well, you're probably wondering, well, why does that make any sense? Because if it completely turns all the way around, it should eventually go back to the same spot, right? So for instance, if it turns right-handed 3 degrees, well, why can't it turn left-handed all the way around until it gets to that point? And the answer is it can. It can. But what it does is that it will go with the lowest number. It will start turning left-handed, it will start turning right-handed, and it goes with the lowest number. That's the best readout that the polarimeter will do, and that's how we properly read what we would call the angle, right? The rotation angle. So this is the purpose of a polarimeter. And Rudolph Research has a polarimeter. They're not the only company that has one. That's just the one that we use. And if I click on the polarimeter, just like we did with the density meter, you're actually going to see a whole thing that shows up here to the top. Our polarimeter looks a little different. It's a little bit older, but it's still very similar. It's probably a different color. Our tags are probably green instead of blue. I guess Rudolph Research decided to make the move to a blue tag instead of a green tag. But I can click the polarimeter product line up here at the very top. And I can go down and I can kind of read what all the polarimeter has to do and the role that it plays in a laboratory. So it says Polarimeter Model Selection Guide. The polarimeter models from Rudolph Research are perfect for chemical, sugar, pharmaceutical, cosmetics, essential oils, education, and university laboratories. So I'm seeing it dabble into a little bit of everything, right? Chemical production, sugar, so I'm working with the food industry, pharmaceuticals, cosmetic industry loves to use it. It's typically organic in nature. Those are the samples that are ran. Great for cosmetic lines. Essential oils, at the same time, to check the purity of those essential oils to make sure it is an essential oil and not just vegetable oil with a little bit of scent added to it. And education in university labs. So there's a couple of lineups. The Autopol is how they'll define it. Autopol 6, automatic polarimeter. And it tells you a little bit about what it can do. Some of these are computer networked. Some of these you can hook up to software. Some of these you can save data on a USB drive. Some of these you can print off. Some has more options than others on the actual user screen. We have a very simplified version, though. We don't need all the bells and whistles on the polarimeter itself. And as you can see as I go through, this is now Autopol 4. The Autopol 4, as far as the screens go, it looks like they get smaller. It's like a cell phone, right? Sometimes they get bigger, sometimes they get smaller. But here's an Autopol 3, and this is very similar to what we have in our laboratory. This is what you would see when you walk into N307 where it's currently housed. You will see a touch screen to the right. You'll see a digital readout over here that you can write down your numbers with. Our screen's probably not that pretty and not that colored. It's probably just a black and white screen, but it's still very similar to that Autopol 3. Okay. All right. Here's the door that opens up, and inside is where we would put our samples. So what would happen is that we would take this sample out, the sample compartment. We would take it out. We would fill it full of our sample. We would look through it to make sure there's no air bubbles. And then we would put that sample in the sample compartment back inside, and we would close the door. Notice I said just back inside. It doesn't really matter where you put it. You can put it up here to the top. You can push it back here to the back. You can keep it right there in the middle. It doesn't really matter, quite honestly. It doesn't use distance as a measurement of anything. So wherever you put it, you should get the same readout. I just like to be consistent when I do them. Okay. All right. And here's an Autopol 1. It says Autopol 1 automatic polarimeter is a single wavelength model with an accuracy of plus or minus 0.02 optical rotation. It's great for food and educational applications where budget's critical, but state-of-the-art quality is still important. It's suitable for non-USP or high concentration pharmaceutical raw material measurement. So this is the polarimeter that we actually do have in our lab. It's an Autopol 1. So again, on a resume, when you begin to use this polarimeter, make sure that you put a Rudolph Research Autopol 1 on your resume so people will understand that you know how to use this piece of equipment. Here are some older versions of some of the polarimeters. These are kind of ugly. They look dated. They're getting replaced with newer and newer models, and we don't have anything that looks like that, for goodness sakes. But, you know, there's some people that do not have an automated polarimeter, and they would love to have one, and this is a very good way, or a cheap way at least, to incorporate one into their laboratory. All right, so the same thing's going to happen here. I'm going to post a couple of videos that I would like for you to watch about the polarimeter. We're not going to be bogged down in the theory about how this works and what happens. I just want you to kind of have a general overview of the purpose of this equipment, and that's exactly what it does. As long as you understand that this machine is used to measure rotation of light, either left-handed or right-handed, from a molecule, then I think that you're good enough. There's no equations we're going to go over. There's no example problems that we need to talk about. It's just a general acquaintance of the instrument itself, and that is it. All right. If you visit the website over here to the right-hand side, again, you'll see some polarimeter videos that I will put in Blackboard that I would like for you to watch. It will talk about the sample cells. If I click on that link, a picture of some of the different types of sample cells will be pulled up. Notice, look, syringes are inside or pointed basically onto the sample cell, and the sample cells can come in different lengths, different materials, different ways to fill them up. Some are stainless steel, some are glass, and you can see through them. It really just depends on what you need as a laboratory. Okay. As far as the polarimeter accessories, I can click on that. It will give me an idea of different cells, maybe some different pictures of them. It will talk to me about dimensions and the purpose of each type of cell, but that's really all that we're seeing here, right? I'm not really seeing an automated auto sampler that gets connected to this thing. I'm not saying that they can't be out there. I'm just saying that they're very uncommon. Most of the time, this is a physical, manual type of filling the solution up, putting it into the machine, reading different measurements that come from it. I'm not saying that you can't have an auto sampler to it, though. Some people probably do, but it is more uncommon to have an auto sampler on this instrument when you compare it to something like a density meter, right? Or some of our other equipment that we have. Okay, so that's all that I want to say about a polarimeter. Again, watch the other videos that I'm going to put up. They're probably YouTube-based. They probably come from Rudolph Research themselves. All the questions will be based on my videos as well as those. Make sure that you take some notes. That way, when you open up that assessment, you can answer those questions without a problem. So, you now know a little bit about a density meter from Rudolph Research, and you now know a little bit about a polarimeter from Rudolph Research as well. So, we'll just keep trucking on. We'll keep picking out pieces of our equipment. We'll keep trucking through them. I'll keep giving you an overview, and that's the purpose of this lecture module.